Hello students, welcome to the fourth lecture on the de-Broglie hypothesis. So today we will discuss different expressions of the de-Broglie hypothesis, wavelength of the de-Broglie, waves attached with a charged particle and neutral particle under different speeds. And then afterward we will discuss some demonstrations on the topic as well. So today's topic is de-Broglie wavelength of a charged particle. So it will have two cases. First, let us discuss relativistic case. An object is said to be moving relativistically if its speed is comparable with the speed of light. Suppose Q is the charge on a particle. V is the speed that the particle has obtained after being accelerated through a potential difference, speed gain. V is the speed gained. And capital V is accelerating potential. Let us say M is mass of object in motion and P is its linear momentum. M0 is rest mass of the object, and we know that the wavelength of the wave attached with particle is given by lambda is equal to h upon mv, which can also be written as h upon p. Let us set this equation number 1. Next, I will assume that initial velocity of the particle, let us say it was 0. Now when it is accelerated by potential V, then the work done on the particle will be given by charge into potential difference, where V is the accelerating potential. And the change in kinetic energy of the object will be given by final kinetic energy minus initial kinetic energy. So the final kinetic energy, let us say it is EF, and initial kinetic energy is EI, and change in kinetic energy will be this one. However, since we have assumed that initial velocity of the object is 0, so initial kinetic energy will be 0, so it will be equal to EF itself, final kinetic energy. Now the final kinetic energy achieved by the charged particle is equal to total energy minus rest mass energy. If I subtract rest mass energy from total energy of the particle, then the remaining energy will be the kinetic energy. So total energy, let us say total energy is E. It will be minus E minus m naught c square. So according to Einstein theory of relativity, E is equal to square root of m naught square c4 plus p square c square. Therefore, the change in kinetic energy, which is equal to E minus m naught c square, will become equal to this quantity minus m naught c square. Let us say this is equation number 3. Now we know that work energy theorem in physics, it tells that the work done on an object is equal to change in the kinetic energy. Therefore, I can write a relation between work done and equation between 2 and 3, that work done is equal to change in kinetic energy. So the left hand side of this equation will be Q into V, and the right side will be equal to m naught square C4 plus P square C square whole square root minus m naught square minus m naught C square. Now I can take this term to the left hand side. It will become QV plus m naught C square is equal to m naught square C4 plus P square C square whole square root. Now we will square on both sides of this equation. Then the left hand side will become QV plus m naught C square whole square, and on the right hand side the square root will go off. It will become m naught square C4 plus P square C square. If I expand the left term, it will become Q square V square plus m naught square C4 plus 2QV m naught C square, and right hand side will remain as such, that is m naught square C4 plus P square C square. Now this term will cancel with this term. So therefore I will have P square C square equal to Q square V square plus 2QV m naught C square, and therefore P square will be equal to Q square V square by C square plus 2QV m naught C square by C square. Now I can take Q square V square by C square. This quantity can be taken outside the integration of this right term. So P square will become equal to Q square V square by C square, and inside the round bracket the first term will give me 1 and the second term will give me 2 m naught C square upon QB. So P will be equal to square root of all this, and since all these three terms are in square, so it will become QB upon C and square root of 1 plus 2 m naught C square upon QB. Therefore, the wavelength of the charged particle accelerated by a high potential difference, so that it gets a speed comparable with the speed of light, will be given by lambda is equal to h upon p. And if I put the value of p from above equation, then we will get lambda is equal to hc upon qv and square root of 1 plus 2 m naught c square upon qb. Now this is the expression for wavelength of a charged particle, de-Broglie wavelength of a charged particle accelerated by a very high potential, so that it attains a speed comparable with the speed of light. So this is in fact a relativistic formula for wavelength of a charged particle. And now let us discuss if a charged particle is accelerated only by a small potential. Means the speed that it achieves is very small as compared to the speed of light. Now that case in which the speed obtained by the charged particle is smaller than comparable with the is smaller than the speed of light is called non-relativistic case. So this is now our second topic, non-relativistic case. Non-relativistic case. Now in this case, the formula for kinetic energy can be written as half mv square, which can also be written as p square by 2m. If I make the same assumption that initial velocity of the charged particle was u equal to 0, then change in kinetic energy, in this case, change in kinetic energy will be equal to final kinetic energy, that is half mv square, minus initial kinetic energy, that is half mu square, which will be p square by 2m minus 0. And work done is given by charge into potential difference. And if I again apply work energy theorem, according to which work done QV is equal to change in kinetic energy, that is p square by 2m, then I will get p square is equal to 2m QV, which will in fact give me p is equal to square root of 2m QV. And now I can find the wavelength of the charged particle by the expression lambda is equal to h upon p, that will give me lambda is equal to h upon square root of 2m QV. Now this is the expression for de-Broglie wavelength of a charged particle when it is accelerated by a low potential. Now this equation can be applied to any charged particle, let us say proton, let us say deuteron, alpha particle, or even electron. The only condition that it requires is that the speed gained by the particle after passing through this accelerating potential must be small as compared with the speed of light. Now in this non-relativistic case, we can have a special formula for electrons only. Let us say the charged particle is electron. If the charged particle is electron, or equivalently it could be positron also, because both of these particles have equal mass and same charge. However, the sign of the charge will be different. One has positive charge, other has negative charge. The positron is positively charged and electron is negatively charged. Now for an electron, the magnitude of the charge is given by 1.6 into 10 raised to power minus 19 coulomb. Its mass, since the case is non-relativistic case, so its mass, whether in motion or at rest, would be almost same. So I can take the value 9.1 into 10 raised to power minus 31 kilogram. Now h is a constant whose value we know, it is 6.63 into 10 raised to power minus 34 joule into seconds. If I insert all these values here in this above equation, then except v, everything is now known to us. So we will get this answer as 12.27 into 10 raised to power minus 10 divided by square root of voltage. This answer will be in meters. However, we know that 10 raised to power minus 10 meter is equal to 1 angstrom. So therefore the expression could be further simplified by 12.27 angstrom divided by square root of voltage. So this is the formula. Kindly remember this expression is valid, number one, only for electrons or positron. Number two, only at low speeds. And this formula is valid for any charged particle, but it has a limitation that it is applicable only at low speed. And the expression that I derived earlier in the relativistic case is the most general formula that is applicable for any charged particle at any speed. Now there is a big question that can come in our mind, that when to apply relativistic case and when to apply non-relativistic case, because if you apply non-relativistic case, then you will have to pay for time, because such calculations will take more time. So we must have the knowledge that how to use our intuition, whether you should apply this expression which is non-relativistic case or the earlier expression which is of relativistic case. For that we have a general thumb rule that if external energy given to an object, if we give external energy comparable with rest mass energy, if we give external energy to an object comparable with rest mass energy of the object, then the speed that object gains, that is v, is comparable with c. So therefore that is helpful in deriving the thumb rule, that when we will apply this non-relativistic and when we will apply relativistic case. Now we just to take care that we are not doing wrong calculations, we will stick to not only rest mass energy, we will stick to 10% of rest mass energy. That is 10% of rest mass energy means 10 by 100 into m naught c square, that will be 0.1 m naught c square. This will be the limit, means external energy given to object less than or equal to this value, the case will be non-relativistic, means you will apply simple formula, and if it is greater than this value, the case will be relativistic. Then you will apply the complex formula. I would give you an example. We know that for an electron or a positron equivalently, the rest mass energy is given by, let us say, for electron, rest mass energy m naught c square is given by 511 kilo electron volt. Now our critical value is 0.1. So what will be 0.1 of m naught c square? It will be 51.1 kilo electron volt. And if I divide both sides by E, that will give me 51.1 kilovolt. It means if an electron is accelerated by a potential up to 51 kilovolt, we can just use this formula. Lambda is equal to 12.27 divided by square root of V, angstrom force. If we are accelerating an electron beam with a voltage more than 51 kilovolt, then we cannot use this formula. Then we have to use relativistic formula. Similarly, for a proton, the value of m0 c square, we all know that it is 931.5 mega electron volt. So 0.1 of this will become 93.15 mega electron volt. And if I divide both sides by E, then I will get the maximum potential, which can be used as accelerating potential, up to which the case will be non-relativistic, and that will be 93.15 megavolt. Now, if the accelerating potential for a proton is up to this value, we can use this formula. Lambda is equal to h divided by 2m qv square root. Otherwise, we will have to use the relativistic formula. Let us take an example. So, if I am given that an electron beam is accelerated by 100 volt, what will be the wavelength of that electron beam? Since 100 volt, this is an electron beam, so my thumb rule is this one, 51 kilovolt. So 5100 volt, 51 kilovolt will become actually 51,000 volt. Now 100 volt is very small as compared to 51,000 volt. So I can simply use this formula. Lambda is equal to 12.27 angstrom divided by square root of 100. The square root of 100 will be equal to 10. That will give me 1.227 angstrom. Answer. This is very simple. Similarly, if I am given the value and that the accelerating voltage is 10,000, let us say voltage is 10,000 volt, then lambda will be equal to 12.27 divided by square root of 10,000, which will be equal to 12.27 by 100. That will be 0.1227 angstrom. I am using simple values just because I don't want to use the calculator in the video lecture, but this thing is applicable for any other complex numerical values. The only thing that you must take into account is that the accelerating voltage must be smaller than that of this 51,000 volt. 10,000 and 100 both were actually smaller than 51,000 volt. Now, what would be the case if I use the accelerating potential to be 10 raised to power 6 volt? Now, 10 raised to power 6 volt is quite large than 51,000 volt. So, I would not be able to use this formula. Of course, if someone uses this formula, 12.27 upon square root of 10 raised to power 6, that person will get some answer. The result is going to give some answer. It is 12.27 into 10 raised to power minus 3 angstrom. This is the answer that you will obtain. Of course, this answer is wrong because the accelerating potential is so high that it has now given the object a speed comparable with the speed of light. So therefore, its actually mass in motion will be very large as compared to its rest mass. We cannot use this formula. If you use, then it will give you wrong result. Then therefore, we must do the answer like this. Lambda is equal to hc upon qv, and it was square root of 1 plus 2m naught c square upon qv. Now we must put the values here to get the final answer. 6.63 into 10 raised to power minus 34 into 3 into 10 raised to power 8 divided by q is 1.6 10 raised to power minus 19, v is 10 raised to power 6 and multiplied by square root of 1 plus 2. M naught is 9.1 10 raised to power minus 31 and c square is 9 to 10 raised to power 16 upon qv. Again it will be, that is 10 raised to power 1.6 10 raised to power minus 19 and v is 10 raised to power 6. Now you can solve this to find the answer, and this answer will be quite different from the previous one. Now if you want to just verify that whether this answer, this is a relativistic case or a non-relativistic case, you can just find the speed of the object when it is accelerated by a voltage of 10,000 volt by using this formula. V qv is equal to square root of, that is equal to its speed will be given by qv, that is equal to m naught square c4 plus p square c square. You can find this formula to find the value of p. That will give you the momentum of the particle. That way, from that you can find the speed also. So it will be comparable with the speed of light. So actually we should actually use this expression in such a case. Let us now discuss the case of a neutral particle, that is de-Broglie wavelength. De-Broglie wavelength of a thermal particle. Like neutron. Now, you cannot accelerate a neutron by applying a potential difference. A neutron can be accelerated only by increasing the temperature. If we increase the temperature of a neutron, it cannot achieve a speed comparable with the speed of light. At least in laboratory, such things are not possible. These may be possible on the stars, but I would not be talking about that. So in that case, we will just apply non-relativistic formula. We will not be able to use non-relativistic relativistic formula. It will be only a non-relativistic formula. So according to that, the kinetic energy gained by the object is given by thermal kinetic energy. We know that the thermal kinetic energy is equal to 3 by 2 kT, and this kinetic energy will be gained by the object, and it will be equal to the value of half mv square. Again, I assume that before giving the thermal energy, the neutral particle was at rest. So this 2 and this 2 will get cancelled. So I will get, if I multiply both sides by m, then left hand side will become m square v square is equal to 3m kT, where m is the mass of the neutral particle. This will become p square is equal to 3m kT, and p will be equal to square root of 3m kT, and therefore the value of lambda will be equal to h upon p, that is equal to h upon square root of 3m kT. Here kindly note that T, the temperature, must be in Kelvin scale. It is the absolute temperature. You cannot use centigrade or Fahrenheit or Richter scale temperature. If it is given in the numericals, kindly convert that into Kelvin scale before doing the calculations. That is only important thing that I would like to tell you regarding this expression. So this was all about the theoretical model of the de-Broglie hypothesis.